Thanks, Scott, for the introduction. So my name's Adam Gerber. I'm a structural engineer from Vancouver, Canada. I work for a small firm. We've had the privilege of being involved in quite a good number of mass timber projects. And so today, we're just going to spend a little bit of time talking about floor vibrations and sort of how we approach it and some of the issues that we've had and how we can navigate our way through to a solution that is in the best interest of the project and in mass timber in general. So by way of a quick agenda, I'm going to give a little bit of a disclaimer. This is a technical presentation, so I apologize if that's not really your thing, but at least you can glean that it's, if you're not technically inclined, at least you can be happy you don't have to do this. So I'm going to start with an introduction to floor vibrations and then move on to sort of a general look at some of the dynamic characteristics of conventional systems and sort of how they perform from a vibration perspective and maybe a little bit of distinction between how mass timber is a little bit different. And then at the end, we'll go through some floor examples with mass timber and time permitting, some design analysis suggestions. So 4 things to remember. You can't really have your cake and eat it too. So a lot of people just say, blanket statement, just add mass, it'll go away. If mass is there, you have to consider it, and we'll circle back on that a little bit later. Stiffness and mass are talked about, and they're represented by the frequency. So when you're talking about the frequency of a floor, you're inherently talking about the combined properties of the stiffness and the mass, and vice versa. Inherent damping is free. Supplemental damping is really expensive. And every person will experience and judge a floor's performance differently, so it's a moving target, which is awesome. So briefly, some sources of vibration: human activity, things like walking, jumping, dancing, potentially vibrating machinery, air conditioners, fans, anything with rotating parts if it's not properly isolated, and external forces such as traffic, wind buffeting, etc. And we're really going to focus on walking-induced vibrations today. So some of the top complaints that we get: sort of bouncy floors, dishes rattling in cabinets. If you have a bouncy floor in the roof, sometimes fixtures will start swinging from the ceiling. That can be pretty uncomfortable for the people below. Floors that squeak, sensitive equipment. And so I promise I'm going to burn through this really fast, but there is a little bit of math just to sort of paint the picture so that we can talk the same language. So dynamic problems, the easiest dynamic problem to solve is a single degree of freedom problem, basically a mass and a spring. And basically what we're talking about is there's a mass term, a viscous damping coefficient, a spring stiffness, and a forcing function. And so mass is always coupled with acceleration, the damping is coupled to velocity, stiffness to displacement, and forcing function is periodic in time. So a few key relationships that we can identify from this is that the frequency is related to the mass and the stiffness, and that was one of our takeaway points. And as I just mentioned, the forcing function is periodic with time. So in this figure, I just sort of thought I would illustrate the relative magnitude of displacement versus velocity versus acceleration. And it really just sort of paints the picture that even very, very small displacements can result in pretty significant and feelable accelerations, which is typically what we measure when we're talking about vibration. So that was the simple problem, and then in reality, of course, there's a lot more degrees of freedom, and so everything becomes a matrix and it becomes quite complicated. But thank goodness we have software to solve this for us, so I don't think I'll ever solve a matrix by hand again. So many people are probably familiar with modal analysis from doing earthquake engineering and dynamic analysis of structures for seismic. And hopefully we can just sort of shift your focus to floor vibrations, and a lot of the principles are virtually the same. So if we take an example of a bridge or a simply supported beam, the first mode shape would be the deflected shape of the beam, and if you sort of push it down and allow it to release and vibrate freely, in the bottom figure you can see that the displacements and the associated accelerations eventually go to 0, and they oscillate back and forth. Of course, real structures have multiple modes, so they can, with varying degrees of energy, going from the lowest energy mode is the first to increasing energy. You get all sorts of mixes of behavior. And essentially, the take-home is that every mode has a natural frequency and one or more locations of maximum response. And the beauty is that we can solve each mode individually and superimpose all the results together to simplify the problem. So the last part of the equation is the forcing function. And so just a quick look at what it means when we say humans are imposing periodic loads on a structure. So here we have a few different time histories of people walking, where they measured the rate of walking and the force that they were imparting on the floor. And I'm not sure if you guys can see the numbers. It looks pretty small on the screen. But I think it ranges from about 1.2 hertz up to sort of the high 2 hertz, which is cycles per second. So a very fast walking pace would be sort of 2.5 hertz. And of course, they come with varying degrees of impact force level as well. So we're trying to capture all of this behavior in some way to predict an outcome. So when we put all the pieces together, basically we have the person on the bridge is the forcing function, we get a modal response, and then we can get some measure, we can make some prediction about the acceleration of the structure. Pardon me, I'm having a little bit of trouble seeing. So a frequency response function is basically if we did this analysis at every potential walking frequency, we could identify which walking frequencies cause the greatest response in our structure. And basically what it is if you're exciting the structure at its first mode, you're getting a very high resonant response at the first harmonic. Typically what we see is that structures are excited sort of in their third or fourth, due to the third or fourth harmonic of a walking frequency. And so we're really dealing with the third and fourth, which is quite a lower amplitude of vibration. The last part of the equation is sort of human perception. So there's a difference if you're standing versus sitting versus lying down, and whether the accelerations are aligned with the axis of your body or if they're normal. And so again, trying to capture all of this complexity in a way that makes sense and gives us a reasonable outcome can still be a challenge. And then for us to be able to make a judgment about whether something's acceptable or not, we need some sort of acceptance criteria. And so this is borrowed from the Design Guide 11. Composite steel structures they've done a lot of work to sort of understand the problem, and they've done a great deal of research and put together a lot of resources, which we will lean on pretty heavily to help us understand the implications for mass timber structures as well. So I think we're pretty much done with the math now, thank goodness. Summarizing a few sort of more familiar structural types for people who are active in this industry. So cast-in-place concrete structures, sort of 100 to 150 pounds a square foot. It's a pretty heavy structural system. 1 to 5% critical damping is pretty typical. Concrete has a pretty unique characteristic where under very small stresses, you actually have higher stiffness than you calculate sort of for typical loading. So due to the very small amplitude of vibration you experience due to walking, they actually recommend increasing the elastic modulus by about 35%. So you get an increase in stiffness and you have the benefit of two-way action as well. So we don't typically expect vibration problems for cast-in-place concrete. Steel and composite structures, sort of middle of the range, sort of 50 to 100 pounds a square foot. It can be extremely lightly damped in some cases, as low as sort of 0.5% up to 5% sort of critical damping. If it is composite, you again get the benefit of that increased dynamic modulus of concrete. And then sort of globally, the stiffness depends on the framing sizes and the layout. Lightwood frame, 10 to 40 pounds a square foot floor weight, so it's definitely a lightweight structure. Damping can be sort of 2 to 12%. And the stiffness, again, it depends on the framing sizes and the layout. Something to note about light wood frame is that although people don't tend to go into a great deal of analysis, we still end up with a lot of really good performing light wood frame floors. And I think a lot of that is due to the industry sponsored research where they sort of took the scope of their problem, did a lot of testing, and they've provided a lot of guidance on how to select appropriate floor joists. So that brings us to mass timber and sort of hybrid systems. So typical mass timber materials, everybody's pretty familiar by now: cross-laminated timber, nail-laminated, dowel-laminated timber, GLT, mass plywood panels, etc. So let's look at how these stack up compared to more conventional systems. So in terms of mass, we're more like 15 on the low end to sort of 65 pounds a square foot for floor weight on the high end. So sort of lightweight-ish. Damping between 1 and 6%, pretty typical of the other systems as well. And the stiffness, again, really depends on the framing size and the layout. One thing that's kind of interesting about mass timber is that people talk about it often being going to be governed by vibration, but then there's not really a lot of guidance on what to do or how to deal with that. So I thought it would be helpful to really burn through a couple of quick sort of ground up examples of a mass timber vibration and sort of typical design process to sort of illustrate where you can potentially run into problems. So in a case where we have mass timber panels spanning between mass timber or lightwood frame walls or whatever the walls may be, in this case chose a 20-foot span, sort of typical concrete topping and typical live load. So it went through and picked a panel based on the deflection requirements, because we do know and we hear often that mass timber is governed by serviceability. So we'll start by sizing for deflection and then check for strength. So we go through our PRG 320 sort of pre-approved layups, and we decide to make it a 2-span continuous to more easily meet the deflection requirements. And we pick a 5-ply panel. Once we've picked our panel, we go through and we check the strength. We find that we're good. And so now we're sort of through the typical phases of design, and the question is asked: what do you do about vibration? How do you assess whether or not it has adequate vibration performance? So the first thing typically to do is to consult the manufacturer's literature, and at the end of the day, the manufacturers have instituted far more projects than any one designer in all likelihood. And so they've heard the feedback from the clients, they've experienced these issues in the field, and they generally have a good idea of how to deal with them in design. So right out of the literature, we can see for the panel that we've selected, I've borrowed this table from StructureLam. They have some guidance on vibrations. And you can see that for a single span panel, it's not going to work, but as soon as you get into a double span continuous, it appears that it's governed by the panel size rather than the vibration controlled span. So it sort of implies that we're good to go. And then, as with all things, needing to read the fine print. So at the bottom of underneath the table, there's a bunch of qualifiers to sort of identify when it's appropriate to use those specified vibration limits, and a few interesting clauses as well about, if you're going continuous, there's a 20% increase in span that you can accommodate, and you can neglect the weight of the topping, assuming it's not too heavy. And so these recommendations were based on a bunch of research done by FP Innovations in Canada, and I think they made their way into the US and Canadian CLT handbooks, and they've also made their way into the CSA 086 timber design code. So it's an empirical method, and some of the stated limitations of this simplified method, basically they studied bare floors with finishing partitions and furniture, but no heavy topping. Vibrations are induced by normal walking, not rhythmic activities. Three is that they're well-supported floors, so we're going to circle back and touch on that, what that means. Well-jointed CLT panels, so making sure that you can cause the panel adjacent to deflect at the same time as the panel that you're considering. And then inclusion of the self-weight of the CLT panels only, so neglecting any live load. And if we use this procedure, we get a few different results, but they're all sort of generally telling us the same thing. From this US CLT handbook, we get sort of about 19 feet. From the Canadian code, we get about 21 feet. And from the manufacturer's literature, it's saying about 20 feet is the vibration governed span. So I think at this point, considering we do meet, I would say that we're spanning onto walls and we do meet the well-supported floor assumption, I think that we've done our due diligence and we probably have a compliant design. So what happens if you want to knock out all those walls, have a nice big open space, and you've already gone through the work and you've sized the panel, and so now all you have to do is size a beam. And so we go through and we size a beam, again for deflection, 30-foot span, check the strength, and now we're back to verifying vibration performance. So here we get into an area where we're no longer necessarily considered a well-supported floor. So if we take the Design Guide 11 approach and we go through and we calculate or try and predict the peak accelerations due to walking, what do we need to know? We need to know something about the mass, we need to know something about the damping, and what is the total system natural frequency. So Design Guide 11 gives us a lot of good resources to sort of help make a realistic estimation of how much load is going to be on the structure. It's definitely not full design load, it's not full superimposed load. It's sort of a pared down version to sort of best represent what you can expect to find in reality. So I think in this case for a little bit of live load and some suspended mechanical and electrical, they recommended combined about 10 pounds a square foot. So we can go through and we can calculate pretty easily what's the self-weight of the system, adding in the additional dead load. And I'm not going to spend any time on these. They're in there just for completeness. But we can calculate the effective weight of CLT and sort of the effective supported weight of a single glue-lam girder. And then we can combine them and get a total supported mass that's going to be activated by walking. The next part of the equation is damping. So again, it provides us good guidance on the different things that contribute to damping. Your bare structural system has some inherent damping, and then sealing and ductwork and fit out ended up at around 2.5%. And then we put it all together and we calculate the frequency of the CLT, the frequency of the beam, and the frequency of the system. And we can see that most people have sort of a sense that somewhere between 6 and 8 hertz, maybe you're getting okay, but below that you probably have a low frequency floor and potentially a problem. So we're at under 4 hertz. So we would expect to have definitely not a good performing floor. So if we run through the calculation, we're at about 2% acceleration of gravity, which is 4 times the recommended limit. So it seemed like a pretty inert change to go through and a relatively simple design change to size a beam. It's a relatively straightforward exercise, but it had a pretty significant impact on the vibration performance of that floor, and it's pretty easy to overlook, and I've seen it be overlooked frequently. So we have a little bit of time for some analysis and suggestions. I've put together a bit of a flow chart, which we sort of use in our office to how do you approach the problem and what are the steps that you go through. And obviously the goal is to stop doing analysis at some point. It's not what we love necessarily. I mean, it's fun every now and then, but if we already know we're good, we definitely don't want to carry on doing extensive analysis. So I'll just go through it really quickly. Basically, doing your sizing for strength and deflection like you always do. Consult your manufacturer's literature and verify that the stated assumptions apply. If they do, you can use those resources directly to choose a vibration-controlled span or if you were already okay, you can keep the span that you had in the first place. However, in cases where those assumptions do not apply, we have to go through sort of a Design Guide 11 approach as a reasonable next step. So we go through and we calculate the frequency, and if we're over 8 hertz, and this I know Scott and I have some debates over, and I think there's probably quite a bit more lively debate to come in the coming years. But at some point there needs to be a cutoff for where you can stop going deeper down the rabbit hole. You shouldn't always have to do a more detailed analysis, and so whether or not that's 8 hertz or 9 hertz or 10 hertz or what that cutoff is, there should be some cutoff where you just say, I'm no longer susceptible and I'm not going to do more analysis. However, if you are under 8 hertz, at least in my case, you can go through the process of calculating the accelerations using the Design Guide 11 methodology, and then sort of working from there. Are the accelerations below the threshold? If no, can you add stiffness? Can you add mass? Can you add damping? And sort of working through that. If none of those work, there are other more detailed finite element methods, and there's very detailed sort of guidance on how to perform that analysis. Some of the resources are listed here. And basically, if nothing works and you can't make anything work, then you really have to go back and discuss expectations with the client. There's not a lot else you can do. So quickly, I have an example from a structure that we were involved in on the specialty engineering side, and just as part of our diligence on the project, we went through and did a quick check of the vibration performance of the floor. And so illustrating the use of the flow chart, does it meet the requirement of a well-supported floor? It was CLT beams spanning 12 feet between, CLT panels spanning between beams spaced at 12 feet on center. And so automatically we're sort of kicked into the not well-supported floor system. And so when we go through and we check the frequency, our CLT panel frequency is about just over 10 hertz. So we'd be pretty comfortable with that if it was well-supported. But the beams themselves were at about 6 hertz, and the combined frequency is 5.5 or so. So that doesn't necessarily mean that it doesn't work. It just means you need to go into a little bit more detail and verify the accelerations. So if we do that, we're at just about 2.5%, which is about 5 times the acceptable limit. So we know we have a problem to deal with. So going back to the team, we looked at, are there options to increase stiffness? Can we reduce the span, increase the beam depth, increase continuity, find a way to introduce some composite action? The answer turned out to be no. So we went on to the next. Can we add mass? Can we, again, make a composite topping perhaps? Again, it was no. This is all post-tender, so the pricing was fixed and nothing was free, it turns out. And then reviewing damping assumptions, we went in with 2.5%, but in order to bring it down to where we needed to be, we'd have to justify something in excess of 10%, and that's just not realistic. So to try and justify that it works, we did a finite element approach, nice little model, sort of modeled all the components with appropriate weights. We got pretty much the exact same frequency that we calculated out by hand and the same participating mass. And 2.5% G, so we were pretty much bang on, unfortunately, with the hand calc from Design Guide 11. So if nothing else, it was a useful exercise to see that the two methods agree. So that forced us to go back and basically have a frank conversation with the client, something which I get to pick up when I go back home. So I think I'm pretty much out of time, so I'm not going to spend any more on the sort of, I've got a few insights from finite element modeling, and there's a lot out there as well. Basically, a few mitigation techniques. If you can activate more mass, it's your friend. If you can add mass without making the system worse by basically making it composite, that can be your friend as well, because you're getting the same frequency but more mass, so you're just reducing your accelerations. Reducing spans is the most efficient way to increase your stiffness. Next to that is increasing your depth. And then if you take account of some fixity from reliable sources like facade connections, that can help as well. So without spending any time on it, timber concrete composites could be a whole session all on its own. It's one good way to add mass and stiffness, and it really helps sort of, we utilize it definitely in cases where we're into a really slender floor. Some continuous bonded systems are being investigated as well. TS3, I don't know if anybody's seen their booth. I think they're giving a talk at the same time now, so I guess you're not seeing them. And I think that's all. So thank you for your attention.
Thanks, Adam.